Hello, fellow problem solvers. So, today we're going to be doing a problem from the British Math Olympiad 2013, round 2, problem 1. The motivation for me choosing this problem is because I saw somebody in the comments put that they're doing the British Mathematical Olympiad. So I wanted to do a problem from there in case they want to prepare for this year or maybe the next if this one doesn't go well. So the first question is, are there infinitely many pairs of positive integers m and n such that m divides n squared plus 1 and n divides m squared plus 1, mn. You should always put x and y or a and b, y, mn. Like they're so similar in their sound. But anyways, now I invite you to try this problem out for a minimum of 20 minutes, ideally 40 to an hour, not more than an hour and a half. If you'd like to go along with us, put your first ideas out on paper for the next 10 minutes. Because here's the big thing, like how do I m divides n squared, n divides m squared plus 1. This plus 1, this plus 1. Can I combine the two? That's my thinking here. Is there a way for me to combine them into one thing? And the answer is, well, when I multiply these two, what do I get? I get that. Both of these are true if and only if, not if and only if, but they're true if n times m divides m squared plus 1, m squared plus n squared plus 1. So if and only if this thing right here is true. And now mind you, if this is true, then both of these are true because n divides this, and then I can get left with m squared plus 1. M divides this, I can get m divides this, and then it divides this, so I can get with m divides n squared plus 1. So this is sufficient and necessary and enough. This is just what we need to prove. And why am I looking at this? Better to have one thing to prove as opposed to two things to prove. That's just a general heuristic. It's not always true, but here it's like a thing I'm going with. It's also easier to work with. So for me here, my thinking is, okay, what are some solutions? Say if I put n is equal to 1, right? What does that give me? That gives me 1 plus this, m divides, so m divides 2, m is equal to 2, it works out well. But that's not difficult. So let's put like something. So there's 1, 1 as a solution, 1 and 2 as a solution. What else is a solution? Let's try to figure these out. What if I set n is equal to 2? Well, then I need 2m to divide m squared plus 5. All right, so now this seems a bit, how do I get this? I need m to divide 5 on one hand. So m is either 1, in which case we have the same solution. What if m is 5? We also get a solution, so we have another solution, which is 2, 5. Okay, that's nice. What about other solutions? What if we put in n is equal to 3? Then we have 3m divides m squared plus 10. What solutions do we have here? Well, on one hand, we need m to divide 10. If m is 2, if m is 1, do we have that? I don't think, no, we do not. If m is 2, we have 14, doesn't work, not divisible by 3. If m is 5, actually would anything work? Because this is 1 modulo, this will never be divisible by 3, so this is just not going to work. Right, this whole thing is never going, because this is 1 modulo 3 and this is either 0 or 1 modulo 3. So we're never going to get 3 divides m squared plus 1. That's actually quite weird. So what about 4? We have 4m needs to divide m squared plus what? M squared plus 17. Now wait, this is 1 and this is either 0 or 1 modulo 4. Again, we don't have a solution here. So what about n equals 5? If we have n equals 5, what do we have? We have 5, m needs to divide m squared plus 26. Well, we know 2 is a solution here, so we don't need to check that one out. Now, m needs to divide 26. We have 2. We don't have a 1. We would have had it here. It's symmetric with respect to m and n. So 2, 5, then there's 13. Now what about 13? 169. That's a big number. 169 plus 26 is divisible by 5. And 26 is divisible by 13, so we're good. 5 and 13 is another solution. Now, is there anything with these solutions that we've come up with that you may notice? So we have 1, 1, 1, 2, 2, 5, 5, 13. We're not looking for all the solutions to this, we're just looking for some. But can we, once we have a solution, can we have other solutions? Like, what is a relationship here? Like, this is, for example, from here to here, this is like 2 times 1 is this. But then this is 2 times, then from here to here. How do I get from here to here? Now that's sort of a question. Can I have some sort of relationship, a linear relationship that gets me from a solution AB, where B is greater than A, to a solution BC, where C is greater than B? Is there any sort of relationship that between these numbers that can work? Like, what is C going to be? And the first thing for me to try is some linear relationship between A and B. Let's see if there's any sort of linear relationship. And if I set C to be equal to, say, XA plus YB plus Z, where X, Y, Z are some integers, what will I get? I'll need to get, so from 1, 1 to 1, 2, I'll get that 2, and this is greater than or equal, like this should hold true everywhere. 2 is going to be equal to X plus Y plus Z. X, Y, and Z should be constant with regards to everything. Okay, so one of these is going to be, okay, there could be positives and negatives. So you have this solution. Now from solution 1, 2 to the solution 2, 5, what do I get? I get that 5 is going to be equal to X plus 2Y plus Z. Okay, this gives me that Y is going to be equal to 3. But let's get the final one when we have, and also, this might not work. I haven't checked this beforehand. I'm not sure if it works. 2, 5, and 5, 13. So now I have that 13 needs to be equal to 2x plus 5y plus z. Multiply this by 2 and subtract. Multiply this by 2, I'll get 2x plus 4y plus z is equal to 10 plus 2z is equal to 10. I subtract this from this, and I'll get that y minus z is equal to 13 minus 10 is equal to 3. If y is 3, this means z is equal to 0. And then from here, I'll get that x is equal to negative 1. And does it work here? Yes, it does. Now the question is, does it work in general? So if we have a solution AB, is another solution where B is greater than or equal to A, is another solution B, and what's it called? We had y is 3 and A is 2. So it's 3B minus, actually not 2, it's 3B minus A. Because it does work here, it does work here, it does work from here to here. Now, does it work generally? So if we have that AB divides A squared plus B squared plus 1, what happens here? I invite you to take 10 minutes and push the problem further, see if this actually then ends up holding true. And here's the next step. So we have that when we check out the next pair, which is going to be, 13 and 2 times 17, which is 34, we see that it does work. So it's hinting at this could be a solution, right? That's what it's sort of like telling us here. We might be headed somewhere nice. We might be headed somewhere good. This might be a solution. Also, a thing that we haven't really looked at is like, what is this times this? That could also be something actually that we should just keep that in mind as we're doing this. Like when this is 1 times 1, this is 1 divides 3. So it's 3 times this. This is 2 divides 1 plus 2 divides 6. That's again 3. Then this is 10. 10 divides 30, again, free. Is it this? This is like 5 times 13, that's 65. What's 65 times 3? 65 times 3 is 195. 25 plus 69 plus 1. We're getting frees again. So it seems not only that we're getting A and the same A and B, but we're having the same K times Mn. Like that's going to be fixed, which is hinting at something. So maybe we can even prove that if this thing right here seems to be difficult to get from here to AB divides A squared plus B squared plus 1. So what is this? Well, this is not nice. That's one thing. So we need to prove two things. That's free. So B squared, B does divide free B minus A squared plus 1. This is not because once you get it out, you get this. This is true if and only if B divides A squared plus 1. Now I'm moving here from one thing to two things. Why? Because now it's simpler. Because now I'm using something I know from before. And if I have A, I have A needs to divide, or here we don't really have A. We have 3B minus A needs to divide B squared plus 1. Now, can we prove this? I think that is the big question now. So 3B minus A, given that A divides B squared plus 1 and B squared and B divides A squared plus 1. Can we prove this? And that B is greater than A. B is also greater than A. That's also, it should be important here. So, how can we get to this? So, okay, we can definitely have an argument here that none of these numbers, none of the pairs will ever be divisible by 3, because if A and B are not divisible by 3, then this isn't, so this other pair isn't. So no pair is going to be divisible by 3. So if this divides this, then it also divides 3 times B squared plus 3. Why am I doing this? To get rid of the B squared. And then maybe we can get to something that we know. So then this 3B squared minus A divides 3B squared minus AB. Subtract these two, and I get 3B plus minus A needs, like this is true. This is a question mark. And I'm getting that the question mark is true if and only if, what is this now? This minus this, I'll get AB plus 3 is divisible by 3B minus A. Is there anything I get here? Anything that we have from the problem statement? To me, it doesn't seem likely. If you find something, let me know in the comments below. But given there's nothing here for me, I'm saying, okay, then let's use a stronger statement to prove. And let's try to prove that. Let's actually try to prove that we can find infinitely many m and n such that 3mn is m squared plus n squared plus 1. And we have these pairs. And now we're going to show we can have more pairs. That if we have a pair AB, that we can go to the pair B and 3B minus A. So now let's do that. Okay, so we have this now. And what do we have? I invite you, if you haven't paused for 5-10 minutes, try to solve it from here. So now let's assume, so m is greater than n. And now we're going to prove that that actually once we put 3m minus n instead of m, that this times m times 3, that we're going to get from here to here. Right, and this is going, that we can infer from here that we can infer this. One way is to do this like algebraically, as I'm doing right now. 3mn minus 1 squared plus m squared plus 1. And now what is this? This is technically 3 times AB, which I can, so this is like 3xy is x squared plus y squared plus 1. So if I put it on the other side, actually what do I want to have left? I want, on this side, I want free mn. Can I get that? Is it difficult to get that? Okay, let's just do the algebra. I'm trying to be too smart about this thing versus in reality I don't need to. Why would I be too smart about this? So this is what? 9m squared minus 3nm. And this is 9m squared plus n squared minus 3 times n, 6mn plus m squared plus 1. The only difficulty here. Okay, so 9m squared and 9m squared cancel out. Oh, 6 and m, and when I move this here, I'm left with 3 and m is equal to n squared plus m squared plus 1. So it means I can get from this solution to this solution. This pair has a bigger sum than this pair. That's a way for you. If like b is greater than a, that's a way to show that these pairs keep increasing, that you're getting new pairs and that you're not going back to some old ones. So, and given this is true, that we can go from this pair to this pair, we are effectively done. We've shown that there's infinitely many. There's 1, 1, 1, 2, 2, 5, 5, 13. Now we can construct infinitely many pairs, and so we have proved this problem. It's a cute problem from the British Math Olympiad, and there was another way we could have done this. So another way we could have done this was to say, hey, look at this. What is this? This is a quadratic in m and n. This is, of course, after you figure out the 3 here. And you can say, okay, wait, this is a quadratic in m and n. So if I know this is a quadratic in, I can look at it as a quadratic in m, say, and I'll have m squared minus 3mn plus n squared plus 1 is 0. So if one solution is m, the other solution by Vieta's rules, if I have the other solution, say x, then I'll have m plus x is equal to what? Well, if you remember, you have ax squared plus bx plus c is 0. Solution is x1 times x2. Like there's one way, there are many ways to prove Vieta's rules. One is if x1 and x2 are solutions, then you can write this as x minus x1, x minus x2 times a is 0. Right, then these two things are the same. And then you see when you multiply through, x1 times x2 is plus c over a, and x1 plus x2 is minus b over a. That's just another way of figuring out these Vieta's rules. So we have this is going to be minus, so it's actually 3n, right? n plus x, 3n. And so we get if this is one solution, then the other one is x is equal to 3n minus m. Right? So this gives you, if you have one solution, you have another one. For me, like what? Now that I'm writing this, I was a bit confused for a second there. Wait, but we had the opposite. But here we're not imposing any sort of restriction, which one's bigger, which one's not. We can look at this as a quadratic in m or n. If you look at it as a quadratic in n, you'll get a different solution. You'll get 3m minus n, which is what we had previously. So this is another way that you could have solved this problem. Or you could have even looked at this totally differently, which I think is a little bit wild, but because there's these Vieta's rules, if there's one solution, that's m, and then the other solution is m times x is equal to n squared plus 1. So the other one is n squared plus 1 over m. So the other way they could have sort of proved this problem, shown that there was a solution, is to go ahead and say, oh wait, so if we have the pair mn, we also can go from here to the pair n and the n squared plus 1 over m. And then I think it's maybe even easier to prove this fact right here. This divides this. But mind you, if you were just reading a solution and they just told you, oh, we can go from this pair to this pair and we're done, you'd be like, wait, what? How did you even, where does this come from, right? You would be like, what is happening here? But in reality, there's a long process of discovery that leads you to this other solution. Also, mind you, even the 3 times m minus n, this also transformation, when you just read the solution, mind you, if I wrote the solution, I would be like, Notice that if mn is a solution, then also this is also a solution. If n is greater than m, then this one will be greater than m. So the sum of these pairs keeps increasing, or the biggest one among the pairs is increasing. And starting from the pairs 1, 2, I can construct then infinitely many pairs just by repeatedly applying this transformation to them. That's also a valid solution. Like, that's how I would write the solution to the problem. But that's not how I came up with the solution to the problem. I came up with it by coming up with, wait, there's a 3, there's a 3, there's a 3, there's a 3. Whoa, there's a 1, 2, a 2, 1, a 1, 1, a 1, 2, a 2, 5, a 5, 13. These keep coming up. Is there anything? Can I get more solutions? Is there a linear transformation from one to the other? That's also a little bit of a stretch for me to say, is there a linear transformation? But you're looking for patterns. A linear one makes sense because okay, I shouldn't really say really, that doesn't really make sense, but it makes some sense because, actually, now that I'm thinking, could you do a quadratic one? Like, if this was applied twice, no, you would still have a linear transformation because it's all at a degree 1. So thinking back, why isn't there a quadratic transformation or a bigger one? And I don't really know right now. My intuition is that because we have, if m was the thing that was a quadratic, the next solution was a quadratic, we need to have m divide n squared plus 1. We could run into some trouble there. So that's why I think it's not quadratic and it has to be linear. But that's just what I think. Let me know what you think down in the comments below. And as always, thanks for problem solving.